Hello, welcome into another video. So I'm preparing, let's say, the coding of Starship and Mars missions. But before actually doing that, I am coding here the missions with this vehicle, which is called SPACE4. So SPACE4, in the end, it's a vehicle that have more stages, more types of engines because um, beyond the normal rocket engines also have advanced jet engines that will allow us to use in some part of the ascent phase. But for the other hand, it's simpler because we'll not need to refuel in orbit and do docking in some into another starship or even to a ring that can facilitate the orbital refueling systems. So let's start. So there are a lot of changes here in the KOS code actually, because first thing it's more a theoretical thing. So if we want to go to Mars, the first thing is to align. We need to be aligned with Mars itself. And in order to do that, what we'll need to do is to make sure that we are in what it's called phase angle. So we need to make sure that, okay, let's see, here it's Earth, so here it's Mars. So we need to be at a specific angle relative to the sun in order to start our journey. So to facilitate that, here when we select that we want to go to Mars, like 04, we'll do these calculations. Um, you can also check the code. It's very easy code and very nice to understand. So when he's asking if we want to process the phase angle, in the end, what he will do is to advance the time in warp mode uh, to the day where we can have an optimal delta V to Mars. So this is what we will do right now. So we will advance in time. So some days will be past and forward. Okay, so right now we are at 24th of August 2022. So we are in the future, of course, to the next window opportunity to travel to Mars. So now, so we are in correct day for launch, but we are not yet in our current, let's say, hour. Okay, so what is the hour about? When we want to do, let's say, a launch like this, we want to make sure that the planes, the orbit planes, are in sync. Okay, and in order to do that and to minimize the delta V needed to match the planes, we need to wait for a specific hour in time where we need to spend less fuel to do that match planes synchrony. So that will happen now. So it's the relative angle to the with Mars. You see, so right now we are 3, 2, 1, 9. It's very good, and it's enough. Okay, here a little bit of lagging with so many things happening. So right now, gear is up. Our vertical engines are off, and we are just flying now as a regular airplane, let's say. So at this phase, we are pitching, or we are trying to pitch into 30 degrees, but we are having a lot of drag. So let's say this will be relatively slow. So now we will try to pitch to 70, As you can see, we are still below Mach number 1.0, so it means that we are subsonic, trying just to gain the necessary altitude to do the first boom. That will start now, and now we are in the phase which is called transonic phase until Mach 1.2. So we are basically in jet mode, so we have all these jet engines. We have 8 jet engines just pushing the ship using the atmosphere, of course, and some nuclear engines to provide electricity to the ship. So now the SB engines are in rocket mode, so yeah, they are just consuming liquid fuel and oxidizer. And soon our jet engines, main jet engines, will not have, let's say, enough atmosphere to burn, and they are disconnected. So now jet engines are completely off, and we are now in a transition phase, just waiting for the vac engine have enough vacuum, let's say, in order to operate with efficiency, and that will happen at an altitude of 52 kilometers. So you just need to wait a little bit. So what we can see here is at horizontal speed. The horizontal speed it's slightly increasing a little bit, but the vertical speed it's decreasing. Okay, mostly because tower thrust weight ratio it's not 1. These engines are powerful but not so powerful, but they do the job. They just have the power needed to sustain more or less the velocity until we reach these 52 kilometers. We are almost there. Okay, and now our vacuum engine, our powerful vacuum engine started, and of course the thrust weight ratio now it's much higher, and as soon as we are climbing, the thrust weight ratio it will increase and increase until more or less about 3.0. It will stabilize more or less about that value. Okay, right now we are trying to climb with this vacuum engine and at the same time with our atmospheric engines. These will be the same atmospheric engines that will slow down us at Mars and will prepare us to the landing. So of course we cannot use them more than what it's needed. So at this point that we reached the apoapsis of 140 kilometers, um, the atmospheric engines were just shutting down, and right now we are okay with this. So recently there are some bugs sometimes with the shadows. Um, in same positions or some angles. Sometimes that appears and sometimes it disappears. Okay, so what will be, let's say, the next step? So right now we are in a phase that mostly we want to gain horizontal speed. Uh, and here we can also control the speed, the vector speed that we have, both vertical and horizontally. And right now we are about 9,000 kilometers per hour, and in order to achieve orbit, we'll need to be about 25. So we are not yet at 50%, let's say, of the speed that we will need. Uh, that will happen relatively soon. Here, okay, now we are pitching for just 2 degrees because our horizontal velocity is already gaining some effects, and we are already have enough momentum to counteract the gravity force. And okay, we have here actually a very nice view, as you can see. It's always amazing, these views. But like I was saying, so we are still keep accelerating. We just should keep an eye always on this value. So this value should always be in the value range between 0 and 2 minutes. And the ideal thing is to have it decreasing from 2 minutes to 0. Because when apoapsis, when we are very near to apoapsis, is when we are increasing the periapsis at the most efficient point. So we are just doing that. So we are in the most efficient point of our suborbital right now in order to have that. Even if you see the periapsis 8, it's increasing very fast actually because we are decreasing the time to periapsis, and that allow us to get orbit relatively quickly. So if we check the speed, we have more or less now the double of the speed that we had at the point where we're checking this. So we are right now at 19,000 kilometers per hour. So it's a very high speed. We are about to change to a new phase, which is completely horizontal, which right now. So when periapsis is greater than minus 3,000 and a half thousand kilometers, so we just keep pitch 0 and the acceleration will just lead us to the orbit. Check time the apoapsis still decreasing, so we are getting better and better orbit. So our suborbital will at any moment pass to a completely orbit. So if you see here, you can also see very nice that here you have our apoapsis, and as soon as periapsis height will get a value bigger than 0, so basically a non-negative value, um, we'll start to go to a orbital flight. Of course that we are just in a secure orbital flight when we are, okay, in this case on Earth, in an orbit bigger than 140 kilometers. So when we are out of atmosphere, and that it's happening now. Okay, now we'll just increase the apoapsis to 1000 kilometers of altitude, which is right now. So to reduce the inclination plane of our orbit to the inclination of Mars orbit. So we are minus 3, 2, 1, 0. So we will burn now at any moment. Okay, and you can see that the inclination is being adjusted, and also here the relative inclination to the target is decreasing. Okay, so now it will maintain and the burn will stop. That's it. So after this, we okay, the code we're doing the calculation to the node. So let's check what actually is being done. If you come here, you'll see that now the node maneuver was calculated in order to do our transorbit to Mars, which is called Trans-Mars injection, and this will be the burn will cost about 3,000 meters per second until we reach the orbit of the sun. This value actually it's relatively close to the trans-lunar injection. It's just a little bit higher because the delta V needs to increase apoapsis in orbit with Earth. It's exponential, it's not linear, and that will be, let's say, observed here during this burn. I will show to you. So let's wait for the proper position using the RCSs, which should be now. Okay. So now we are at proper position, doing our prograde burn. Okay. So when we are doing a prograde burn in this direction, apoapsis will increase in this direction. So here we have the relative scale to the moon, and we can also see the moon current altitude in relation to the Earth. And as you can see here, we already used almost 1/3 of our delta V for this node, and it seems that we are in the same position. So that's why I said that uh, the delta V needed to increase apoapsis it's exponential. So you can see we are at the same position, of course, and the apoapsis didn't increase so much. So now we are about half. So imagine we used half of our burn and our fuel needed to increase this, and then the other half will put us outside uh, into Earth escape from the gravity sphere of influence of Earth. So 25 million meters, or if you prefer 30,000 kilometers. Okay, so check. We are completely ending now the delta V and the maneuver, and it seems that we are starting, but it's not that, it's the opposite. So look, 350, 300, 200 meters per second to go, and here we go. Okay, so we passed the altitude of the moon. Okay, so let's see. This is a nice picture. Of course, now we are warping towards to the orbit of the sun and getting out from the Earth gravity sphere of influence. Okay, and that will happen here in 4 days. Actually, we can now look to the moon. Okay, moon it's relatively closer, so it's closer from us than Earth. So Earth looks relatively smaller because of the distance, of course. And it's a nice shot because at this time we had the moon from this side of the orbit. Okay, so we are about to reach our sun orbit. That's it. So we are in sun orbit. So the code what we'll do right now, it's a correction again to the to correct the planes. So that can now be seen here. So we have just a slight relatively inclination, which is 1.84 degrees or 85 if we round it up. And this will have now a slight correction because um, we are not in the optimal position, which is the ascend node and descend node. So because of that, we will not be able to do a full um, correction, but will be the correction needed to do the next burn. Okay, and that's it. So now we are just waiting for the prograde. Okay, and in this burn, we will do the most of the work uh, to get higher apoapsis 8 relatively near to Mars orbit. And after that, we will do uh, another burn to do a correction to intercept Mars. So this is the first burn. Uh, okay, the interesting points here, it's of course the apoapsis. This is Mars. And what you can see here is the current separation if the burn would stop at this moment. But of course, the burn will not stop, the burn will increase, and the separation to Mars will decrease. We can also check here. Uh, okay, not that, but here we can also check the velocity in orbit. It's also interesting in the end to see this. This is what we will see soon at distance that will decrease. Okay, sometimes this happens. There's a lot of fluctuation in what will be the closest point, but will tend to stabilize. Of course, that there are always 2 points. When two circles intercept, there are 2 points. One is here and another point is there. And sometimes it's just swapping between what will be the first point or what is the correct point to match this approach. Okay, and right now we are there. Okay, so now we already calculated our node, um, which will do interception with Mars orbit. So this will be our last burn, let's say, to intercept Mars. So what we have here, we have the the maneuver node in 24 days. So we'll just increase a little bit. Um, And with this we'll be at this distance of Mars. So 547,000 kilometers to Mars. And at that altitude we will do the retrograde burn in order to orbit Mars. That it's the next maneuver. Okay, so we are reaching our point to do our current burn, to do Mars interception. 4 hours, 3 hours, 2, 1. Okay, and that's it. So this burn, it's relatively cheap now. It's the, let's say, the precision burn that will do the most important work. Okay, visually, what we can see here is the current apoapsis and the desired apoapsis. So when these two values will encounter, will be there. Another thing that we can do is to observe the delta V that it's needed, or just check it here also because it's the same value. But this is useful in order to avoid to have our navball here um, during the map view. Okay, so we are still have 300 meters per second to go. 200. 100. Okay, and we are there. That's it. So interception was done with success. Um, now it's just a matter of going there. So now this is not interesting, and this is now the current interesting view. So what we have here, it's the distance that we have to Mars. Um, in this orbital mechanics, everything it's happening in arcs, and this is not like we are used to do. Just go straight uh, as a straight line. It's not. Of course, that imagine if you are here looking to Mars from a telescope from the ship to Mars, it looks like Mars it's coming to you into your direction apparently, because we are both traveling in some um, very similar horizontal speed. We are traveling in the very relatively near inclination plane. So we have the illusion that Mars is coming to the ship, or we are going to Mars. But in the end, what is happening is just this. So the orbits um, are just in interception course. Okay, we are about 40 days to intercept Mars. 30, as we can see here. 25, 20, and imagine once again, if you are looking Mars at a telescope, you would see Mars coming. It depends of the perspective that we are seeing things. So, okay, now entering in gravitational sphere of influence of Mars. Now we are waiting to the periapsis in order to allow our maneuver, our braking maneuver, to be more efficient. So 3.5 hours to go. 2. Now it's a matter of minutes. Okay, and we are doing the burn. So what we want to do, it's decrease now the velocity vector in this direction in order to allow us to have a Mars capture orbit. So let's wait for the burn. This is what we call a capture burn. Increase just a little bit the simulation speed, just a little bit. This time and distance to Mars escape will need to decrease or to increase to 3 days more or less, and then between 3 and 4 days, and will be relatively near to Mars orbit. As you can see now, we are not warping anymore. Now we have a fast change of Mars escape point, and it tends to be now in curve, tends to be circular. Mars is here, and okay, we are there. We are at the Mars orbit. So in an ideal position, what we would do, it would just wait for the periapsis, but here we don't want to waste 4 days or 6 days to go to the periapsis, which is in the other side, and so we are doing this from the apoapsis, which is also a possibility, and will save 6 days in total. Okay, so now our periapsis, it's relatively slightly below 300 kilometers of altitude, and now we are just waiting to get there to do a burn that will put us into a circular orbit into Mars. Okay, this is an interesting view actually. So from here, now we can see Mars approaching. Here we see the time that it's still remaining to reach our periapsis, which is the lowest altitude point that our orbit have right now in relation to Mars, of course. So let's wait here a little bit. Okay, we are getting there. And here we are. So if we look, you'll see that the apoapsis is decreasing very fast because we are in the optimal point to decrease it, which is of course the periapsis. So now we are just waiting to decrease of apoapsis. And after this burn, basically, we will initiate the landing sequence. Okay, that's it. Whoa. So now we are starting the landing phase. So we are in this phase 3, which is called the descending phase. So where the most important goal of this phase is decreasing the horizontal speed, because we are passing from a orbital trajectory to a suborbital trajectory. And to doing that, the main goal is to decrease the horizontal speed, and that will lead to the consequent increase of the vertical speed. So, and we were doing that until a phase where actually vertical speed will start to increase again. And at that point, we'll just keep the engine with a minimal power, just to avoid continuous discontrolled acceleration. Okay, so I will pass to the radio altitude instead of just altitude. We're going to increase the warp a little bit. So our vertical speed it's 130 now, almost. Okay, now we are in that phase where we are actually decreasing. You see, like I said before. So at that moment that we started to decrease speed, we just reduced the engines, and right now we are just going slowly accelerating towards the surface, but we can never pass some maximum vertical speed that it's defined here in this variable. So this is the maximum vector speed that we can have, and this is the current vector speed that we have. So as you can see, this is not this speed, it's not this orbit speed, but it's actually the surface speed. Okay, so if I put here on surface, you understand it better, but for now I'll just keep it here in orbit. It will change automatically anyway. It was just that remark. So, and more or less until we reach 100 kilometers of altitude, nothing's changed, let's say, dramatically here. Everything is smoothly. So as you can see, we are keep increasing our vertical velocity. So everything is as it's supposed to be. And as probably you can feel, we are reaching the phase where we will not use anymore the warp speed. So I will pass now to the normal speed, because things will happen rapidly, let's say. Anyway, I will take now the opportunity to open the TC mod. I'll put the QoS now here. Okay, so what happened is that we decrease the maximum speed for 700 to 500 meters per second. And this is done in iterations, step by step, and every time that we are entering in a new phase of the landing, this speed will decrease, and then the adjustments will be done in that sense. Okay, here in the end we are waiting for altitude 80. Yeah, and at that altitude we will switch to SAS mode, and we are now seeing a similar velocity of the one that is here. The surface vector velocity. Okay, our horizontal speed, it's still decreasing. If you have paid attention to the horizontal speed, we are just reducing the horizontal speed very smoothly during all the phase of the landing. So I will prepare here the windows to the next phase in order to be ready at that time. So again, now we decrease the maximum speed to 300, and this is where we are. And now 200, and we are going to 200. Okay, the need of this is that at any moment our current vacuum engine will not have, let's say, enough vacuum to operate, and then we'll need to switch to the atmospheric engines, let's say normal engines. And when we will do that, those engines don't have a so powerful thrust weight ratio, so we should not be let's say in a vertical velocity higher than 200 meters per second. So that's why we always see these corrections being done to make sure that the transfer of power when will happen relatively smoothly. Okay, and that should be the next phase in our landing. So as you can see right now, we are about 30 kilometers of altitude in relation to the surface, because here we are measuring the real altitude to the ground and not the normal altitude of the planet. Okay, 25 kilometers of altitude, or of 8 if you prefer a more correct term. Okay, now we switch to these engines, and now this is the atmospheric engines that will do the job. Please note that these atmospheric engines were the same ones that were putting us in, let's say, were doing in Earth during the launch, put us from a trajectory to apoapsis bigger than 140 kilometers. So that's why the fuel is at half right now, because we're the fuel used at that time to do that phase of our launch. So now we are waiting to be at 7,500. When that will happen, so we switch from vertical descent to horizontal descent. Actually, this is the opposite of Starship. Starship will do the opposite, changing from horizontal to vertical. But this ship, this SPACE4, will do the opposite. Okay, 9,000, 8,000, and 700. We are almost there. Okay, at this phase, what this will do, it will decrease the velocity of descending to a comfortable velocity to do the swapping maneuver. Okay, this ship it's very heavy and it's important to do this. Okay, 10 meters per second, we are okay. On, set course, direction, down. And that's it. Everything looks good. So we have a maximum speed of 50, which is what we are doing right now. Um, Something is wrong. No, okay. 20 now, maximum speed. We are trying to reach our desired. Okay, good. Now our maximum speed is 6. It's relatively hard to achieve. Okay, now we are. Oops. Okay, and that's it. Here we are. We landed. So I hope that you had enjoyed, and in another future video, um, I will explain how this SPACE4 ship um, will construct a colony on Mars, and what are the steps and why this ship is so advanced, why it have here a ground assembly line, why it have here a workshop, okay, and why we have all of these special things, why we have apartments, special places to have food, special drills. This is actually a very complex machine, and that will be explained in another video. So I hope that you had liked. Um, so I'll see you in another video.